All right, so here we are at packet 6, class number 6 for 2021. Let's see what's happening. Meet table 4, which would be on meet one of you, but we pushed that back to Thursday, so we'll do that Thursday. Went around and checked 6.1. Today I checked 6.1. That, oh, that's old, sorry. Right here, 6.19. Check see. You all, for virtual, your 6.1 is due Sunday night. Sunday night. We're going to kind of, I think we'll probably finish it. I'm hoping we'll finish it by Friday. So I'm saying tentatively due Sunday night, but we got to wait till everyone's done with it, obviously. We're going to go over every one of those, okay? But we're not going to do 10 today, so it'll be 10. It'll be Thursday probably. Then, so I tell you the truth, Sunday night is too early. We won't be done. So eventually, sometime next week, you'll have to submit it because we're getting stamps for it. So to make it equal, you're going to have to submit it for probably quite a few points, at least 30, probably more. So it's worth a lot of points. But keep after it, keep up with it on 6.1. So speaking of 6.1, here we are. Let's go ahead and this is what we did to start off the class. I sent them all to the board to show me what they knew about number 9. So I can't send you guys the board, but let's go ahead and I think we may have, no, we didn't start it. So let's go ahead and work on this one, the helium balloon. Now, what we might have done, and stop me here if I'm wrong, I thought we had done some stuff on this. This is the way it'll look on the practice problems. By the way, the practice problems will be available tonight on 6.0. Sorry, for the take home, for the test, not take home, for the test 6A, there are 2 sets of practice problems. The first set is tonight, available on PDF. I'll have paper copies available tomorrow. So if you just want to wait and then wait till tomorrow to come to my front porch, you can get your packet back. You can get your test back. You can pick up, say it's copied off, you can pick up a paper copy of the practice problems. So that might be worth your journey over here. But on that, this is the way the problem's set up. It's set up where you're first supposed to, like your prep stuff. This is like a little prep area. So your prep area, you're supposed to give me the symbols, the forces involved. I'll give you this hint, there's 4 forces. The forces involved with this helium balloon, and a little bit about their direction, okay? So let's start the chat up here. And on the chat, I want you to list for me, we've done this before. No, we did this yesterday. Did we do this yesterday?
Yeah, we did this yesterday.
What? We did number 9 yesterday? Well, then where?
When we started it, you gave us the forces.
Oh, okay. So confused today. Gosh. All right, so we gave the 4. Hi, Feder. Okay, so if I gave you the forces, here they are. We have mg down, and when you're something else maybe we didn't talk about. But when you're doing this came up today. Also show the direction. So mg down, buoyancy, B sub A is always straight up. Always straight up. You can count on mg by definition being straight down. It tells you what vertical is. Plumb bob. Buoyancy, I don't care whether it's water or air, any kind of buoyancy is always straight up, never at an angle, okay? Force of lift is sometimes straight up, but it could be at an angle. Normal force, probably 90%, no, 75% of the time straight up, but could be at an angle. Buoyancy, never at an angle, always straight up. We also have force of wind, F sub W, and that one, it says from the left. So it looks like that. And then we also have, well, I know it's going 10 miles an hour, and I said that air drag starts at about 30, but that's for a car. A balloon is mostly air, right? Mostly area. It's like a huge profile area. So with a balloon, the rule of thumb is you always have drag, always. So R sub A, R sub A. And that always opposes motion. So it's going to be in this direction. Okay. Now that we've kind of established what we're looking for, those are our puzzle pieces. Then we go over here and we say, okay, let's go and get our direction of motion, which is 80 degrees above right. Well, I only know it's above right because the wind's blowing from the left, it says, left to right. So, I make this sucker. You don't have to get a protractor out, but maybe guesstimate it here. Get a ruler, please. Let's make this look. I don't want slop. I mean, really, you guys are beyond this kind of. Just I see students do this still. There, and there's my 3 body. That's disgusting, folks. That's disgusting. You're gonna get laughed out of any respectable college classroom if you pull that. Then they're gonna say, "Where are you from?" Don't say Norman High, please. Say Norman North. It's embarrassing. So get a daggone straight edge. I mean, you guys are pretty good about it. Looking up here, you guys are all pretty good about this. There's a few students in class that could use some manners when it comes to doing a free body diagram. Okay, so that's my direction of motion. And don't do a big fat arrow. That really just works on cars and stuff. But I show the plus up here. It's not always up. Sometimes you want down to be the direction of motion, but we're going to go plus up, plus to the right, plus. Okay. And then now we established that. We go ahead and start sticking our forces in there. Doesn't matter which one you start with. The old traditional is usually mg. But mg in this case, let me get rid of that. I don't need that now. Mg it's a balloon, for goodness sakes. It's a helium balloon. Someone asked once, a helium balloon, well, I put that on a scale, we can't weigh it. It has mass. There's mass of helium inside it, and there's the latex of the balloon or mylar. So yeah, it has weight, but it's small. So mg down, okay, not a big arrow. We have buoyancy up, a lot of it. Because that's one thing, you're a little kid, you let go of your helium balloon, that sucker is gone, and then you are crying for the next 30 minutes. But you don't have time to grab that thing. Buoyancy is a powerful upward force for balloons. Unless it's just your air. If it's your air, maybe not. But a helium is really light. So that sucker goes. We'll spend almost a whole time on buoyancy later. I'm just introducing it right now. So there's B sub A. And then we have force of wind from the left. Just put an arrow in there. Force of wind. And then we have air drag down. And air drag always opposes motion. So it's in the opposite direction. All right. Now, is everyone happy with this? Give me a thumbs up or a thumbs down if you like it or don't like it. I need to survey the audience.
Don't you have to put your direction of motion?
That is my direction of motion. And you go, well, how do you know for sure? Give me a thumbs up. Okay. Well, because the wind is blowing from gusting from the left. So if the air is blowing from the left, it's going to the right. Therefore, the balloon's got to go to the right, right? The balloon's not going to go to the left if it's wind's blowing from the left. Like, oh, the wind's out of the north. Well, I'm not going to, balloon's going to blow south. So yeah, that's the right direction. Okay, true. That's 80 degrees. I could put the degrees in there, but that's okay. It's wrong, by the way. This is wrong. My drawing's wrong. Anybody see what's wrong with it? You may not notice it unless you're going to do head to tail. Head to tail this is one of the reasons for head to tail. is it shows that we're wrong here. Typical student is not going to notice that's wrong, but it is wrong. Very wrong, actually. All right, I prove it to you, huh? Okay, so this is all stuff we did in class. So I'm gonna prove it to you why it's wrong. I'll do some ghosting. FW, I'm gonna draw its ghost. I'm not gonna use a ruler or anything, but I'll draw its ghost up here. I'll sketch its ghost as I drew it. There's FW. Okay, you rewrite it. I'm going to go head to tail. This will be my starting point. Okay. Now, then I draw MG down. I'm going to add that. MG down, about like that. Then I'm going to draw RA back. And RA is parallel because it's the same direction. RA looks like that. Now, when I draw, and that's MG, and that's FW. When I draw the resultant vector, that goes to the very beginning to the very end. Uh-oh. Uh-oh. Wrong. Why is that wrong? I'll put wrong in there. Wrong. What's wrong with it? It is accelerating. So I know there's, I'm going to take a picture of that. So I know there's summation of forces. Now you tell me, why is that wrong?
There's no ghost for their summation of forces.
Good point, but let's save the files. Okay, so no, not in this guy. I don't need it. I don't need that. Sometimes I do. I don't need this. I don't need that ghost because that's just a resultant. That's the final resultant, and it goes from. It's like you had to with that with conservation of momentum because you had to slide that last momentum. Here it's just summation of forces. So in this way, it's actually simpler than conservation of momentum. But there's something drastically wrong. If the direction of motion is 80 degrees above right horizontal, the summation of forces is in the direction of motion. That is not, that's not 80 degrees. That's 80 degrees. So this is wrong. I can fix this drawing by changing one thing. There's a whole lot wrong with it. I can fix it all by changing one thing. Anybody see what I can change? It's a puzzle. What can I change to make it work?
Force of wind.
I could, okay. You can change the force of wind. How? You can't
make it smaller.
Yes, you can't change the direction, but you can make it smaller. Let me show you what I mean. So I'll take a picture of that so I can erase it. Erase all that stuff. Erase all the those ghosts. Erase that. And now I'm going to cut back on that force of wind, way back. So force of wind looks like this little tiny thing. Didn't say how, it says gusting, but didn't say how big it was. Force of wind. And then my ghost is now looking like this. This is the process. This is what separates people that are from Norman High than from Durant, Oklahoma, because they don't go into this kind of detail. But this is what you got to know in college, kind of how to do a proper free body. So there's force of wind. Now when I throw in the mg, I come down right to there, right to my direction of motion. Then I come back with the RA, opposite direction of motion, RA, mg, force of wind. Then my summation of forces is where it should be. It's in the direction of motion. It's at 80 degrees. Boom. So that's how head to tail can give you a feel for the lengths of these vectors, all right? And draw it properly. Okay, so that's the right way to do it. Now let's go through and get some equations out of this. I'll give you a minute. Let me hit pause so we're not wasting their time. But I'll give you a minute to pause, share, pause recording. Okay, recording. Okay, so I'm recording. I want you guys, if you're watching this at home, I want you to come up with the equation for the summation of force in the x So Newton's second law in the x direction and Newton's second law in the y direction for this particular problem with correct angles, okay? So now I will hit pause. Recording. Okay, so we're back, and the studio audience there has made their guess. Let's see what we're going to do. So we go, okay, in the x direction, I have all the wind, force of wind. I don't get any mg. I don't get any buoyancy, but I get a portion of the RA. What part of RA? I don't say F force of wind minus RA. It is minus. In fact, if you ever see that you're adding drag, you made a mistake. Drag always, it's something called the work kinetic energy theorem. Drag always drains energy out of a system. So it always takes, it's always what's called a retarding force, okay? A retarding force, meaning that it slows things down. But I don't get all of RA. What part of RA do I get?
RA cosine of 80.
There it is. Thank you. Cosine of 80 degrees equals MAX. So I only get a portion of it. Remember, cosine for the x, sine for the y. So we do the same thing in the y. I get all the buoyancy. I always, it's like OCD, but I always put my positive forces first and then my negative forces. And I always put the whole force. Like if I get the whole force, I put the components. It's just me. It's just OCD. Minus mg, all that one. Then I get a component of drag. Minus RA, now sine, right? Sine of 80 equals MAY. Now, if you can do all that on your own, you're pretty good shape. You're pretty good shape in my class. I don't expect you to be perfect at this yet. We're just learning it. But we'll do some more practice. We'll be practicing this all year, the rest of the year. It's about 6 weeks. Okay. Now, that's it. Any questions on 9 before we go on to little Henry? I got to show you Henry. Okay. Now, I told Henry I'm going to put him in a physics problem. So Henry's my one of my little neighbors. We got these little kids in this neighborhood. I'm going to stop sharing this screen and just give you another one. New share. Okay. You don't have to stop it. You just go new share. Learn something. Here we go. I'm going to share that one now. Okay. This is Henry. I put this on our Facebook group. You may have saw it. And I just happened Saturday. I was up here writing a test and I hear this Zoom go by, a bunch back and forth, back and forth. I look at the window and there's old Henry. His dad had rigged up, this kid is amazing, man. He is always breaking his arm or something. Or we got a black eye, or this kid is just full of spit and vinegar. And so here he is, riding by my house. Maybe. Oh, huh? So his dad had rigged up the air blower, the leaf blower, to the back of his skateboard. And Henry can kind of vector that thing as well and do a little steering. And so here he is. Well, I thought that is thrust. That's exactly what thrust is. See, there's air coming out the back. It's blowing out the back. That's your escape velocity. You're losing air particles. This is like a closed system. You're losing air particles. It's sort of a closed system. It's not quite, because you are pulling air in from the atmosphere. And so he's pushing out air out the back. It's kind of recoil, right? Recoil, Newton's third law, and thrust all go together, all right? And so there he is, cruising along. There's old Clyde. Clyde's always like 2 or 3 steps behind everybody else. I love Clyde, man. He's a great kid. Anyway, Clyde running alongside him. Hey, Henry, let me do it. Okay, so that's, let me do a new share now. Go back to this. So that's where I want to write. I want to derive the equation that goes with that. Okay, so let's get off this and go to your cheat sheet, because I can see, I think I'm putting this on the practice problems, maybe in the second set of 6A practice problems where you have to derive the thrust equation. Okay, so here's the thrust equation. It is the force of thrust equals m dot VE. Now that's a simplified version of it, but it's good enough for us. The force of thrust is equal to m dot VE. Now that m dot, that's Newtonian. Below little notes here, that's Newton. Remember we talked about x dot is velocity, v dot is acceleration, right? So that's Newton. If you go to calculus though, you'll do it Leibniz method, which you would say dm dt times VE, and that's Leibniz. We've talked about this before. Okay, but normally for some reason, we use Leibniz all the time.